So, okay, starting off with our topic of electrical quantities, right? So, when we talk about electrical quantities, there are the quantities that you need to know is you need to know what is electrical charge. You need to know what is current, what is voltage, what is power. And these are the four major ones that you need to have an idea about. So, starting with electrical charge, right? How do we actually define charge? The way you define charge is that charge is basically a characteristic, or you can say a unit of a matter that shows the extent to which it has more electrons or less electrons compared to protons. So, charge basically shows you how many more or less electrons there are compared to protons. If you have more electrons compared to protons, so the particle gets negative charge. If there are less electrons compared to your protons, the particle gets a positive charge. So charge is simply, it's a characteristic, or it is a unit of any particle, any matter, that shows you the amount or the difference in protons and electrons, right? That's what charge actually is. So charge is measured in the unit of coulombs. And the electrical charge that we see on one specific electron, this value is fixed. The charge on one single electron is negative 1.6 into 10 raised to the power of negative 19. Now, this negative technically will not affect your calculations that much. The negative is simply telling you that the charge is it's negative. It is the electrons are more than the proton, which makes sense because this is an electron. But in this particular case, in our calculations, we don't have to worry about the sign itself too much. The value of the charge, though, is going to be quite important. Now, this is the charge on one electron, 1.6 into 10 raised to the power of negative 19. When we talk about any piece of a conductor, so our conductors are going to be pieces of metal. Since you have not done chemistry, let me go over with you. So a conductor is generally, metals are considered to be good conductors of electricity, but metals are considered to be good conductors of electricity. But that does not mean metals are the only compounds or the only substances that will conduct electricity. We also have materials known as semiconductors. We will study them later. Semiconductors also conduct electricity. So I just want that to be clarified. We have the topic of semiconductor. We'll go with them. Just wanted to clarify that metals are good conductor of electricity, but that does not mean that non-metals cannot conduct electricity. Those non-metals that can be classified as semiconductors. So a good example of them is your graphite, your the lead in your pencil, and another good example of this is silicon. These are all non-metals, but they can still conduct electricity to a certain amount. So before we talk, we're not going to talk about semiconductors right now. We'll go over them later. Right now, we're just going to talk about conductors. Why is it that conductors actually, or your metals actually conduct electricity? The reason your metals actually conduct electricity is because a metal is made up of positive ions that are surrounded by a sea of delocalized or free electrons. So the positive ions, for example, my wire is made up of copper metal. That wire that is made up of copper metal, it is going to be surrounded by copper ions, positive copper ions, and then there are going to be free delocalized electrons that are going to be all around the positive ions. So what happens is that whenever I will apply a potential difference, I'll explain what potential difference is later. Whenever we connect it to a power supply, this is my piece of wire that I have connected to a battery. This battery is connected to the negative terminal and the positive terminal. Now, the negative terminal of the battery is going to repel these electrons. The positive terminal of the battery is going to be attracting these electrons, right? The negative terminal of the battery will repel the electrons. The positive terminal of the battery is going to attract the electrons. As a result, the electrons are going to move from one area to another. They will move from one end of the wire to the other. This is why metals are able to conduct electricity, because whenever I will connect a power supply, these electrons are delocalized, they are free, they are available. So whenever I will connect them to a power supply, they will move from one side to another. So, what is a piece of metal made up of? A piece of metal is basically made up of positive ions surrounded by these electrons. Now, let's say I come up to you and I give you this piece of metal and I say, can you please tell me what will be the overall charge on this piece of metal, right? So, how are you going to calculate the overall charge? You will say the charge on one electron is 1.6 into 10 raised to the power of negative 19 coulombs. There are a total of 10 electrons, 20 electrons. I mean, obviously, they're not going to be 10, 20. They're going to be like, in power 23, power 24, right? 10 raised to the power of 23, 10 raised to the power of 24. They're going to be like lots of them. But technically, we'll say that total number of electrons are, let's say, 10. So if I take the total number of electrons and I multiply them by the charge of one electron, I can find out the total charge, right? So I can also figure out the total charge by using this formula. Q is equals to NE, where N stands for the total number of electrons that we can find in any metal or any conductor or any sample that you're dealing with. And E would be the charge on one single electron. And so in 1 coulomb, generally, we have this many electrons. In 1 coulomb charge, we have 6.25 into 10 raised to the power of 18 electrons. Okay. So these many electrons, when they come together, they give you a charge of 1 coulomb. So we can figure out whatever the total charge is simply by taking the number of electrons and multiplying them by the charge of one electron. Now, this formula you're not going to be using quite a lot. I've seen maybe like very few questions on it. There are not a lot of questions that utilize the using this particular formula. Okay. Now, when we talk about our electrical quantities, so one of the easiest electrical quantities that we can talk about is electrical current. What is electrical current? An easy definition that you might have talked about is current is rate of flow of electrons. Or actually, let me correct myself. Rate of flow of charged particles. That's what current is. Rate of flow of charged particles. Now, when we're going to talk about it, this was the diagram that we were taking a look at. I told you that whenever I will connect my battery to any conductor, the electrons will be repelled from the negative side and they will be attracted towards the positive terminal. So the electrons will move from the negative terminal towards the positive terminal. This flow of electrons, if we take the flow of electrons and we divide it by time, we will be able to calculate current, right? So if I take the charge, the total charge, and I divide it by the time, that gives me my current. My current is equals to whatever my total charge is divided by per unit time. Current is basically, to be very honest, it is simply the rate of the movement of your electrons or the rate of the flow of charged particles, right? How fast these electrons are flowing. The faster the charge is traveling per unit time, the greater the value of current. The faster the charged particles are moving per unit time, the faster your, the faster your, the faster your charged particles are moving, or the uh, per unit time, the greater your value of current is going to be. Do not confuse this, by the way, with velocity of the electrons, right? Current is quite simply put how much charge is going or traveling per unit second. That's what it is. How much charge is being carried per unit second. That is what current is. So how much total charge is there per unit second, that gives me the value of current. Current is measured in amperes. Charge, as you know, is measured in coulombs, and time is measured in seconds. Now, here I want to mention one thing. We need to remember that coulomb, is not an SI based unit. Coulomb is a derived unit. Amperes, on the other hand, is an SI based unit. You have 7 SI base units, right? You have, I believe you have meters, you have seconds, you have amperes, you have Kelvin, you have mole, you have candela, which is for the intensity of light. And I believe there's one more, which I can't remember right now. So there's 7 SI units, right? Any other unit is going to be a derived unit. So I just wanted to clarify that coulomb is not the SI unit of charge. It's a derived unit. The SI unit will probably be ampere second, because you get questions on this where they ask you to figure out the SI units. So I wanted to clarify this. So when we talk about the rate of flow of charged particles, please notice that I'm saying charged particles and I'm not saying electrons. Why? Because your electrical current can also be generated by the movement of your positive particles as well. Okay, and it can also be generated by the movement of both positive particles as well as your negative particles. When we are going to go ahead and we're going to talk about it. So if I just give you a quick example, for I told you that we can see the movement of your that electrical current can be due to movement of both positive and negative particles as well, right? Charged particles. I'm not going to go over details of that because that is complete chemistry. But when you talk about your battery or you talk about your cell, so inside the battery or the cell, we have a setup in which there is two metals and then the positive and the negative ions are flowing, which leads to the formation of electrical current. So we can also have the formation movement of positive and negative your charge particle as well, right? And we can also have your um, we can also see this where the your so the definition is that it is going to be the rate of flow of your charged particles. Uh, um, okay, so this is what current is. Now, after current, another important electrical quantity that we have to go over is voltage. Now, there are three terminologies that are often used interchangeably. I will explain you the difference between them, but we can technically use them interchangeably. The concept behind them is pretty much the same. First, we have a broad statement or a broad terminology that is voltage. Voltage is like a broad wording or a broader way of classifying it. Voltage simply tells me how much energy is being transferred per unit charge, right? This is what voltage is, how much energy is being transferred per unit charge. Now, voltage is often used interchangeably with two other terminology. One is electromotive force and one is potential difference. Now, both of them are wordings for voltage. Both of them are fancier way of saying voltage. So, but why? What is the actual difference between them? The difference between them is quite small. Without going into too much detail of it, we use electromotive force when we talk about the voltage of a battery. So if I'm going to talk about voltage of a battery, right? So instead of saying the battery is giving me a voltage of 12 volts, I will say the EMF of the battery is 12 volts. I am still talking about voltage, but since I'm talking specifically about a battery, I use the terminology electromotive force. And when we talk about a load, whether that load is a filament bulb, whether it is a resistor, whether it is some kind of thermistor, LDR, whether it is, your microwave television, it doesn't matter. When I talk about the load, so I use the term, instead of saying voltage across the lamp, I simply say potential difference across the lamp. That is basically the difference between the two terminologies. Electromotive force or EMF is now, now that we have the basic difference down, electromotive force is basically work done per unit charge, because this is a battery. This battery is supplying power. It is supplying energy. It is moving these electrons from one side to the other, because these electrons would not move unless I connect a battery. If I connect a battery, the electrons will go from one side to the other. It causes the electrons to be repelled from one side and attracted to the other side. So it is going to be applying a force, right? This battery is going to be doing work on these electrons. If I take the work being done by this battery on these electrons, I will calculate EMF. Keeping in mind that this is the same thing, I will be calculating voltage, right? But EMF, the reason we call it electromotive force is because the battery is applying a force that is causing the electrons to move from one side to the other. And since we're applying a force, so of course there will be work done. So work done by the battery in moving one single charge is going to be what EMF is. Potential difference is energy being transferred per unit charge. And this is, as you can see, even in terms of formula, it's the same thing, because work done is the same thing as energy transferred. Work done and energy are equal to each other, right? So the only difference that usually comes is in terms of terminologies. EMF is when I talk about the voltage of a battery, and potential difference is a terminology we use specifically when we are talking about our um when we are talking about uh, any load or any electrical component that is actually using up that energy. So in that case, we use energy transferred per unit charge. The formula is the same, right? So the difference is basically in terminologies. And you can always just use the word voltage. These are all interchangeable. You can use them. There is no difference when it comes to actual calculations or the formulas that you will use. Now, when we talk about the unit for voltage, so the unit for voltage is of course going to be volts. Also, please remember that voltage is not a SI derived unit either. SI base unit. It is also a derived unit. So you can be asked what is the SI unit for volts. Now, potential difference can be measured, EMF voltage is measured in volts. Now, there is another unit that is electron volt, but do not confuse because it says volt in it. Do not think that this is a unit to measure voltage. It is not. Electron volt is not the unit to measure voltage. Electron volt is the unit for energy. So for energy, we can have two units. We can either have joules or we can have electron volt. What is electron volt? Electron volt is simply the potential difference. When we talk about it, electron volts is basically the energy, right? The energy that is being the energy that we see when a potential difference of 1 volt is applied to one electron. Okay, so what is the energy transferred when I take, because I know voltage is equals to energy per unit charge. If I rearrange the formula, my formula becomes energy is equals to charge multiplied by voltage. So what if I apply a voltage of 1 volts to one single electron? How much energy is being transferred? That is what electron volt is, right? So if I take my voltage and I multiply it by the charge of one electron, I can find out the energy transferred, and the unit for that is going to be in joules. Okay, so I can actually, because energy is equals to voltage upon charge. So if I find out that if I apply a potential difference of 1 volt to 1 electron, what is the energy? So this is the energy, 1.6 into 10 to the power of negative 19 joules. Now, if you want to convert if the unit given to you is electron volts, converting it into joules is quite simple. Simply multiply it by the charge of 1 electron. Do what I did. Use this formula. So you will be able to convert your electron volts into joules. If you ever want to convert your joules into electron volts, so in that case, you will have to take your energy and divide it by the charge of 1 electron. Okay. So if you want to convert your joules into your hold on, give me 1 second. So if you want to, so your hold on, did I say it the right way? 1 electron volt is equals to 1.6 into 10 to the power of negative 19 joules. This is the conversion that you can go ahead and remember. So, if you want to go ahead and you want to convert your electron volts into joules, right? You can simply go ahead and cross multiply. So the way you can convert your electron volts into joule is, like I said, multiply whatever value of electron volt has been given to you by the charge of 1 electron. So you will be able to get your answer in joules. And if you want to go ahead and figure out or convert your joules into electron volts, so all you have to do is that you have to divide your whatever the energy is in joules by the charge of 1 electron. So this is how you do the conversions. If you multiply the electron volt by the charge of 1 electron, you will be able to calculate it, convert it into joules. And if you divide it by the charge of 1 electron, you can convert joules into electron volts. So electron volts is simply another unit for measuring your energy. Okay, it's not a unit for measuring voltage, it's a unit for measuring energy. So there are 2 units for measuring energy. One is joules and one is electron volts. And electron volts is simply telling you how much energy is being transferred to an electron when you use a voltage of 1 volts. Got it? Making sense so far? Is there any question that you would like to ask?
Yeah, everything makes sense.
Okay. All right. So then another really, really important quantity that we have to go over is resistance, right? Before we talk, let me actually explain to you what resistance is, because I'm quite sure you've been hearing the terminology so far, but I don't know if you understand what is the actual concept or what it actually is. Resistance, quite simply put, is the opposition to the flow of current, right? That's how you can define it. The opposition to flow of current. Now, what actually is your resistance? To understand that, we go back to our diagram. Now, remember how I told you that the electrons will flow from one side to the other, and the flow of electrons is actually what leads to the generation of electrical current. What is going to happen is this, that as these electrical electrons are going to be moving, you can see that obviously they're not going to be traveling completely straight. They are going to be going around to the positive ions, and as they do so, they are going to be colliding and bumping into each other. Whenever they will collide with each other, they will lose a little bit of their energy. That will cause the electrons to slow down, and that is what resistance is. That's what resistance is. The slowing down of the electrons. I'm not saying that the resistance is only affected by the number of electrons. But resistance is basically whatever factors, whatever reasoning there might be. Resistance, quite simply put, is when these electrons are colliding and bumping into each other. And in the process, they will end up losing some energy, which will cause them to slow down. Hence, that will cause the flow of current to decrease. When we talk about the flow of our resistance, right? So, resistance, when we talk about our resistance, so your resistance is obviously explained by Ohm's law. Ohm's law states that the voltage and current are directly proportional to each other, provided that provided that resistance and temperature remains the same. There are two criteria. Resistance has to remain constant and temperature also has to remain constant. Now, why temperature? Why is temperature so important? Because again, what will happen if I increase the temperature? If I increase the temperature, the electrons will gain kinetic energy. As they will gain kinetic energy, they will move faster. The faster the electrons are going to move, the more they're going to collide and bump into each other. The more they're going to collide, the more they will lose their energy and the more they will slow down. So temperature leads to increase in resistance and decrease in current. So hence, if we talk about Ohm's law, we need to make sure that temperature remains constant, because if temperature is not remaining constant, the resistance will invariably increase and current will also decrease. So the criteria for Ohm's law is that the as the chart criteria for Ohm's law is that voltage and current will be directly proportional to each other, provided that resistance and temperature are going to remain constant throughout. And if we plot a graph, we will actually see a straight line going through the origin, which is the criteria of seeing a directly proportional relationship. One, it has to be a straight line. Secondly, it has to be going through the origin. That's the criteria. Now, the graphs that we draw are with current on the y-axis and potential difference on the x-axis. That's how we draw them. Current is on the y-axis and potential difference is on the x-axis. Why exactly is it like that? The reason it is like that is because current is, technically speaking, the independent variable. And sorry, potential difference is the independent variable and current is the dependent variable. I apply potential difference. I attach a battery, right? I attach a battery. I apply potential difference. I will supply the voltage. Because I will be connecting the circuit to a battery, because I will be supplying voltage, I will be supplying energy, I will be giving work done per unit charge, that will lead to the electrons moving from one end to the other. And that will lead to the generation of an electrical current. So electrical current is a dependent variable. What does it depend upon? It depends upon the voltage, right? And general rule of thumb, because you're also giving unit 3 exams, that's why I'm going over this. The general rule of thumb is that we try to put the independent variable on the x-axis and dependent variable on the y-axis. So current is on the y-axis and potential difference is on the x-axis. Why am I going over this in so much detail? Because we need to understand one important concept: the relationship of the gradient of the line to resistance. What is the relationship of gradient of the line to resistance? You know
1
that,
over the gradient.
yes, exactly, correct. So you know that, that's perfect. I don't need to go over it, right? So your reciprocal of gradient is going to be your resistance. Why? Because if you calculate the gradient, you are going to do current over voltage, right? But resistance is equals to voltage over current. So gradient, if we do the reciprocal of gradient, we will be able to calculate the resistance. So just I want you to remember this, that whenever you're doing calculations from your graph and you're using the gradient of the graph, because they might sometimes give you a curve like this, and then you have to draw a tangent and calculate it. So if you're ever in that kind of a situation, do remember to take the reciprocal. Okay. Now, Ohm's law is the formula for that is V is equals to IR, where resistance is, of course, going to be in ohms. Again, this is not a base unit. So resistance is going to be what? Resistance is going to be in ohms. This is the relationship that we are going to see in any resistor that is an ohmic resistor or a fixed resistor. Okay. Any resistor that has a fixed value of resistance will give you a graph or a relationship like this, and you can solve all questions related to it by using V is equals to IR. Now, there are certain resistors that tend to have different values of resistance. We call them variable resistors. There are 4 variable resistors that you need to know about: filament bulb, diode, LDR, and thermistor. Talking about the filament bulb. So a filament bulb actually gives you a curve, as you can see, and it does not give you a straight line relationship at all. Why exactly does the filament bulb give you a curve? Because how does a filament bulb even classify as a variable resistor? Because this is not something whose resistance should be changing, right? It's a bulb. Now, what is initially you're going to see that initially it actually seems to have a sort of a straight line situation going on initially. But as the potential difference continues to increase, the graph starts to become a curve in both situations, whether going up or down. So why is it that initially it seems to be following Ohm's law, but then it turns into a curve? This is because as the voltage increases, the current in the wire also increases, the current in the filament bulb. As the current in the filament bulb increase, we need to understand that current has a directly proportional relationship with your temperature. Okay. So what is going to happen that whenever we're going to see a large current going through any appliance, there is always going to be a risk of it heating up. Okay. So the filament bulb is going to heat up because of large current passing through it, because current often turns into heat energy. Right. So when you talk about your voltage, whenever you're supplying voltage, some of that energy is being used in the movement of the electrons, and some of that energy is wasted. We consider it to be wasted energy in the form of heat energy. And that's why whenever we want our filament bulb to be a good bulb, we try to minimize that loss as heat energy. So the temperature of the filament bulb will increase. We have already studied about how increase in temperature leads to what? Increase in temperature leads to increase in resistance. So the resistance of the filament bulb will increase. And if we take a look, see, initially the gradient and the gradient later on. Initially, the gradient of the curve is quite high. As the potential difference continues to increase, the gradient of the curve reduces. And since gradient has a reciprocal relationship with resistance, so you can see even from the graph that the filament bulb tends to have a low resistance initially, but that resistance increases as the potential difference increases. That is due to increase in electrical current, that leads to increase in temperature, that leads to increase in resistance of the wire. So that is why, since the resistance of the wire increases, the gradient of the curve falls and it starts to become flatter. So a filament bulb is a type of a variable resistor that is, but the reason its resistance is changing is mainly due to the uh, conversion of your energy into, so instead of being, some of the energy is being converted into electrical energy, and then some of it is being converted into heat energy. So basically that's what happens. So that's a filament bulb. Then another really important variable resistor that we have is a diode. You might not understand the concept of diode completely right now, because diode is made up of a material known as a semiconductor. So, for a semiconductor, we will do the entire topic of semiconductor, not a whole topic, but we will be talking about what semiconductors are. So then it might just make a bit more sense to you. But a diode, quite simply put, so what are semiconductors? I told you semiconductors are substances. They're non-metals basically that allow the conduction of electrical current up to a certain extent only. So a diode specially is made up of a semiconductor that works in this specific way that it works in this specific way that it only allows the electrical current to pass through in one direction. If we remember what alternating current is, we can have two types of current. We can have direct current and we can have alternating current. Direct current is current that will only be traveling in one direction. We have to also remember that current is a vector quantity. So direction is quite important. So when we talk about it, we can have when we talk about our electrical current. So this is what alternative current looks like. And alternative current is going to be going forward, backwards, forward, backwards, forward, backwards. When we draw a graphical representation, we show it as positive, negative to show the change in direction that is actually going to be taking place. The graph for direct current might look like this, or it might look like this. Okay, both of these are direct current. This is just steady direct current, right? Direct current that is giving you constant value, something you might see coming from a battery. This is also direct current because notice that the direction is staying positive throughout, but it's just that the numerical value is changing. So this is what normally we have. We can have direct current or alternating current. Now, so current can be in forward directions as well as in backward direction. A diode is an electrical component that will only allow the current to travel in the forward direction, right? This is what the symbol of a diode is. You can draw a circle around it or you cannot draw it, up to you. So whatever direction the diode is pointing in, the arrow of the diode, that shows you what current it will allow to pass through. So if the diode is like this, it will allow the current traveling in the right direction. If the diode is arranged like this, then it will allow the current traveling towards the left. Okay? So the arrow of the diode will also always tell you in which direction the current will be allowed to pass through. Now, why does a diode work the way it works? You don't need to know details of this, uh, but you will still understand to a certain extent. You might not understand it completely, but you will understand a little bit when we're going to talk about semiconductors. This is what the curve for a diode is going to look like. So you can see that when my voltage is negative, there is no current traveling through that particular diode. When my voltage becomes positive, the current passing through the diode, initially it increases slowly, right? Initially it increases by a small amount. Initially it increases slowly. Then, after crossing a minimum voltage, after crossing a minimum voltage, it suddenly increases by a very rapid amount. You can see that the resistance becomes almost infinite because this is a very, very steep line, a very steep line. It's almost vertical. It's almost vertical. So the resistance of the diode will become close to infinite. It will become as less as, I'm sorry, it will become zero. I'm saying infinite. The gradient will become infinite. So of course the resistance will be zero. It's an inverse relationship. The resistance will become close to zero, as close to zero as possible, right? And the current will increase rapidly. So this minimum voltage, right? The minimum voltage required that causes the current to increase rapidly within the diode, that voltage is known as threshold voltage. And generally, the value is around 0.6 volt for most electrical appliances, most diodes. This value is around 0.6 volts. So if you manage to get past 0.6 volts, the current increases very rapidly through the through the diode. All right. Now, after this, we have to go over what we call as our thermistor. What is a thermistor? A thermistor is an electrical appliance. I'm saying appliance, I'm sorry, electrical component that also can vary its value of resistance depending upon the temperature of the surroundings. Temperature of the surroundings. Now, thermistor is also made up of semiconductors, specifically silicon. Hence, a thermistor works much differently than the electrical components we studied beforehand. I told you that the temperature increases, resistance increases. That is something that applies to a conductor that's made up of metal. Okay? Semiconductors work differently than metals. Hence, in a thermistor, the relationship is actually opposite. High temperature leads to low resistance, and low temperature leads to high resistance. So, this relationship is different from the relationship I taught you previously. And the reason you see this difference is because of the fact that the thermistor is made up of a semiconductor and not a conductor. Hence, it works on a different principle, right? And we will do semiconductors, so you'll understand that when we go over them. This is the curve. Now, this is the curve for a thermistor at a specific temperature. Because at each temperature value, the resistance will change and you will end up seeing a different graph. You don't need to know any other information regarding than what we have just gone over. Like you don't need to know anything more about thermistor. You might need to talk a little bit about the semiconductors and how they work, but they will not give you any numerical calculations as such related to it. Yes, Ashwish?
How can the voltage and the current be negative?
How can the voltage and current be negative? The voltage and current can be negative because your electrons can travel in both direction depending upon the positive and negative terminal. When we talk about a battery, so for a battery, it's easy for us to visualize because we have a fixed positive terminal and a fixed negative terminal. But what about the main supply that is coming to your house at the moment? That main supply that is coming to the house at the moment, it is set up in such a way that the positive and negative terminals are not fixed, right? Since the positive and negative terminals are not fixed, so based on the fluctuation of positive and negative terminals, the current can either go towards the forward direction or they'll go towards the backwards direction. So, depending upon the terminals, even if you keep on fluctuating the terminals of your battery, you will still end up seeing the same result because the direction of current will depend upon the voltage. So, depending on the voltage, right? So, if when we talk about it, so when we are going to talk about it, right? So, what is going to happen? That the power supply that comes to your house, the power supply basically that comes from your power station, that comes with electrons that are traveling in both directions. So initially they will go forward, then they'll go backwards, they'll go forwards, and they'll go backwards, they'll go forwards, and they'll go backwards. So that is what leads to the current having both positive as well as negative direction.
What do you mean by the current going up and down?
Simply that the direction of, because when you talk about your, okay, so current is a vector quantity. Just like any vector quantity, the numerical value as well as the direction are equally important, right? Now, when we talk about our voltage, there can be two types of voltage. Okay. The two types of voltages that we can have our direct current voltage. Direct voltage means that the positive and the negative terminal are fixed. For example, like your battery. Okay. Now, when we go ahead and we are going to talk about it, hold on, give me 1 second. Okay, so what actually happens is this. Okay, so to understand this, first let's talk about how is electrical current generated. One way of generating electrical current is battery. What is the second way? That generally happens in our power stations. We use a generator. Now, if you remember electromagnetic induction, the topic of electromagnetic induction that you might have done in your IGCSE physics, a generator, we will be doing a generator as well. So no, I think we will be doing a generator. So generally what you have is that you have your magnetic field. In your magnetic field, you have a coil, and what happens is that you are going to rotate this coil. When we rotate this coil in a magnetic field, an electrical current is going to be generated in this wire. Okay. Now, when the electrical wire rotates, actually, Ashwesh, let me just see your course. I think we have to study this anyway. What is going to happen is this, that as so this is, for example, the positive and this is the negative. Now, what happens that as the this coil is going to rotate in the magnetic field, so as it, for example, if it's rotating clockwise or anti-clockwise, what happens that this the electrical current is going to be the electrical current being generated is going to be induced in different directions. Now, why is the electrical current being induced in different directions? That is the entire topic of electromagnetic induction. Okay. The entire topic of electromagnetic induction has that. Why exactly is the electrical current being induced in different directions? The induction of current is going to depend upon the movement of the coil or the force we're applying on the coil, as well as the direction of the magnetic field. Based on these two things, the current is going to be induced. Since the coil is constantly rotating within the magnetic field, so the direction of the current that is being induced in this wire is constantly changing. And as a result, the current that is produced is alternating current. The direction of the current is going to be going positive to negative on constant frequency. So on constant frequency, the based on the number of oscillations of your coil per unit time, a current is going to be generated, which is going to be going like this initially, and then after a certain time period, the direction will reverse and it will be traveling this way. That's where the difference comes. So it can be traveling left to right or right to left, right? So because alternating current is something that we generate, it's not something we actually get from, like we can't connect a battery and get alternating current. Alternating current is what we get when we use our generators in our power stations. That's where alternating current generally comes from. That's why to your house you get alternating current, because when we use our generators, so in a generator, the electromagnetic induction principle leads to the induction of electrical current that is going to be changing in direction due to the constant rotation of the coil in the magnetic field. And since the direction of electrical current that is being induced is going to depend upon the direction of the magnetic field as well as the rotation of the coil, so that is constantly changing. Hence, the current that is being generated from the power stations tends to be traveling left, then right, left, then right, left, then right at a constant frequency. So that's what alternating current is. Is that a bit more clearer now? Exactly what alternating current is?
Yeah.
Okay. So when we talk about our, so this is what you need to know about your variable resistors. Okay. Now, when we talk about Yeah, we have to go where okay. So when we talk about our resistance of any material is going to depend upon three things. What are the three things it depends upon? It is going to depend upon the material itself. Okay, it's going to depend upon the material itself. Then it's going to depend upon the length of the material, and it's going to depend upon the area of the material. Now, let's see why resistance is affected by these three principles. First of all, why is it affected by the material? I told you that resistance is the collision of electrons with the positive ions that causes those electrons to slow down, right? So the electrons, as they're going to be colliding with the positive ions, those electrons are going to be slowing down. And that's what resistance actually is. Now, certain metals may have more delocalized electrons. Some metals may have less delocalized electrons. Why does that happen? Now, that is going to depend upon the chemistry and the property of the metal itself. Okay. Especially when you talk about certain metals, if you ever look at a periodic table. So, in a periodic table, there is a certain group of metals that we call transition metals. You'll find them somewhere over here. These transition metals especially can have different charges. So they can have two delocalized electrons or one delocalized electron. Some of them can have three, some of them can have seven. Why are the number of delocalized electrons different? That is very complicated chemistry. But so metals can have different number of delocalized electrons depending upon their certain properties that they might have. Now, the one of the factors, I'm not saying this is how it's all 100% is, one of the factors that you and I can think of is, oh, the greater the number of delocalized electrons, the more bumping and collision there probably is likely to be. So the actual resistance of that metal is likely to be higher. If I take a piece of copper and I take a piece of iron, I might end up seeing that they might have different value of resistance. Now you might say, but miss, I took the same sample. Like I took the same length, I took the same area, I took same everything, but why are they giving me different values? Because both of them are different materials altogether. Since they're both different materials altogether, they might have different number of electrons. They might have other different properties that might be present over there that is affecting the movement of the electrons. So that property of the material that affects the resistance of the material is what we call resistivity. That's what resistivity is. So the resistivity is the property of material that leads to opposition of flow of current, the property of the material. And as long as you're using the same material, the resistivity will not change. You take a piece of copper and you can make it into a hammer, a pot, a pan, a wire, whatever you want. Its resistivity will not change because the material is the same. Okay, one point I would like to mention is that what I just said, that resistivity is going to be constant based on the material. This is again a statement that is being said at constant temperature. Temperature can affect resistivity even if material is the same. Okay. So, but resistivity is the property of the material. As long as you're doing the experiment at the same temperature, so resistivity will remain the same if you keep using the same material. So material will affect the resistance. Then it depends upon the length of the material. Greater the length of the material, greater the resistance you are going to see. And that makes sense because longer the distance the electrons have to travel, the more likely they are to collide and bump into each other. The more likely they are to collide and bump into each other, the obviously higher the resistance of the material is going to be there. Then it depends upon the area. Greater the area, the more space your electrons have to travel, the more they will be spread apart and the more they will be further away from each other. Hence, you will see less collisions are going to be taking place. On the other hand, if we talk about a smaller area, so the same number of electrons, but now they are forced into a much smaller area. So they're more likely to collide into each other, and they're more likely to lose energy in that process, and they're more likely that you will see higher resistance. So resistance depends upon these three factors. So if I want to calculate the total resistance of any material, I can take its resistivity. Resistivity is measured in ohm meters, multiplied by the length of the meter, and divided by the cross-sectional area. Since wires are considered to be cylinders, so your cross-sectional area will simply be pi r square, right? So your cross-sectional area will be pi r square, and you can calculate the total resistance by taking the resistivity, multiplying it by length, and dividing it by the area of that particular sample. You'll be able to calculate whatever the total resistance is. Uh, any confusion so far? Anything that you would like to ask?
So resistivity is just like how
Yeah.
much the electrons collide with other ions or other electrons.
Okay, Ashwish, technically speaking, it's a lot more complicated than that. The collision of the, so basically, yes, it's the property of the material. What is the what word was I thinking? What is the inherent resistance of that material, because the material itself will also oppose to a certain extent what the flow of electrons is. It might depend upon density, it might depend upon the number of delocalized electrons, it might depend upon any of those things, right? So the inherent resistance of any material is what we call resistivity. So that's basically going to be the inherent resistance, the ability of that specific material to resist the flow of electrons. That is what we actually call as your that's basically what your resistivity is. So the flow of electrons and the electrons bumping into each other, that is just in a way of explaining that how is it that a different material can have different resistance. That's just a way of explaining what it actually, how does that happen. But that's the basic concept of it, but it is multifactorial. It is going to depend upon multiple factors like density, like, the number of delocalized electrons, and a lot of different other things.
Yeah, makes sense.
If you want to ever just think about how to define resistivity, you can simply say resistivity is a measure of the resisting power of a specific material to the flow of electrical current. If you ever want to define it, that's how you can define it. And if you actually, a better definition would be if you say resistivity is the electrical resistance of a conductor um, of unit cross-sectional area and cross-sectional length. That's what basically resistivity is. How much resistance is any material going to have per unit cross-sectional area and per unit length? That resistance is basically resistivity. Okay. Any other questions? Anything else that you would like to ask?
No.
Okay. Okay, Shwish, we'll go ahead and we'll stop over here for today. In this topic of electrical quantities, we're just left with talking about the transport equation, the how we calculate the velocity of the electrons, and we need to talk about how semiconductors work. Other than this topic, you have two more topics. One is your parallel and series circuits, which I believe you might already know quite well from IGCSE. There is not a lot of new information to it. We will go over it, but I don't think you'll find that topic that difficult. Then we have this topic. We have to go over power, energy. And then a new thing that we need to go over is what is internal resistance. Internal resistance is different than resistivity. So internal resistance will be, I believe, something that might we need to go over. Other than that, the parallel and series circuits calculations, I think you'll be okay with it. And power and energy as well, you have their formula, so they're usually okay as well. So we'll stop, I think, over here for today, and we can continue with this topic in the next class. And I have messaged the